For most of computing history, data fitted on one machine. Your customers, orders, and inventory lived in a database on a single server, and when it got slow, you bought a bigger server. That worked for decades, and for most companies, it still works today. Then, a few organizations hit something new. They were trying to index the entire web. There is no bigger server for that. Every page on the internet crawled and processed repeatedly is not a problem you buy your way out of. The machines that could even attempt it cost a fortune and still had one of everything. So the alternative was many cheap machines instead, which sounds obvious and was, at the time, mostly theory. Nobody had software that made 1,000 unreliable computers behave like one reliable one, and unreliable is the operative word. One server fails rarely. Run 1,000 cheap ones, and something is broken all the time. A design that assumes machines stay up never finishes a job. In 2003 and 2004, Google published 2 papers describing how they had solved it internally. One described a file system spreading data across thousands of ordinary machines, keeping several copies of everything, so losing a machine lost nothing. The other described a way of processing that data called MapReduce. They published the ideas without the code. A developer called Doug Cutting, building an open-source web crawler and facing exactly this problem, implemented both. He named it after his son's toy elephant, Hadoop. Hadoop had 2 halves, a distributed file system storing data in chunks across many machines, typically 3 copies of each so failures were survivable, and MapReduce, the processing half, worth understanding because everything since has been a reaction to it. MapReduce made you express work in 2 steps. First, map. Look at each record independently and produce a key and a value. Counting words means the word becomes the key and the number 1 becomes the value. Every machine does this on its own slice. Then, reduce. All values for the same key are brought onto one machine and combined. All the ones for a given word arrive together, and you add them up. And between those 2 steps, the system physically moved data so matching keys ended up together. Remember that, because it never went away. This genuinely worked. Companies who could not process their data at all suddenly could, on hardware they could afford, with failures handled automatically. Hadoop was not a stepping stone people tolerated. For years, it was the only thing that did the job. But it had 3 problems, and they compounded. The first was disk. Every MapReduce job read its input from the file system and wrote its output back to the file system, not to memory, to disk, then copied to 2 other machines for safety. For a single pass, that is a reasonable trade, but real work is never one pass. Our fraud pipeline reads swipes, joins to merchants, filters, aggregates, joins again. Each step was a separate job, and between every one, the entire intermediate result was written to disk in triplicate and read back. And one category of work makes this catastrophic. Training a machine learning model means passing over the same data hundreds of times, adjusting slightly each round. Under MapReduce, that meant reading the same unchanged dataset off disk hundreds of times. The data never changed. It got reread anyway. The second was rigidity. Everything had to be shaped into map and reduce. Some work fits beautifully. Plenty does not, and expressing it meant chaining jobs together, each writing output for the next to read. A pipeline that is conceptually one flow became 5 separate jobs, and nothing could see across the whole thing to optimize it, because each job knew only itself. The third was startup. Tens of seconds before any work began, irrelevant for an overnight batch, fatal for exploring data interactively. So in 2009, a research project at Berkeley asked an obvious question. Memory had become far cheaper than when these ideas were designed. What if intermediate results simply stayed in memory between steps? Pause the video because there is an immediate objection, and it is the interesting part of the story. Memory is not durable. That was the entire reason for writing to disk in triplicate.
If you hold intermediate data in memory and a machine dies, it is gone. So how can that possibly be safe? The answer is genuinely elegant, and it is the idea Spark was built on. Do not copy the data. Remember how to make it. Spark keeps a record of every step that produced every piece of data. Read this file. Filter it this way. Join it to that. So when a machine dies and takes memory with it, Spark needs no spare copy. It reads the recipe, sees which steps produce the missing piece, and recomputes only that piece. Safety without triplication. And because the recipe exists before anything runs, you get something else free. The whole pipeline is visible as one thing before a single row is touched, so it can be optimized as a whole rather than as 5 blind jobs in a row. That combination changed things. Data in memory across steps, a rich set of operations rather than only map and reduce, and a plan that sees the whole job. For work passing over the same data repeatedly, the difference was not a few percent. It made practical what had not been. 2 honest corrections, because the popular version of the story is wrong in both directions. Spark did not replace Hadoop. It replaced the processing half. For years, Spark ran on top of Hadoop's file system, using its storage and resource manager. What it replaced was MapReduce. Today, Spark more often reads from cloud object storage, but that is a separate change. And Spark did not throw away MapReduce's ideas. Group by a key in Spark, and data is written out, sorted, sent across the network, and gathered on the receiving side. That is MapReduce's shuffle, inherited almost exactly. Spark's advantage is not avoiding that step. It is not forcing you back to disk in triplicate between every one. So, that is the shape of it. Data outgrew single machines, so it was spread across many cheap ones with copies for safety. MapReduce made those machines usable at the cost of going back to disk between every step. Spark kept the distribution and the shuffle, dropped the disk round trips by holding results in memory, and made that safe by remembering how data was built rather than duplicating it. Which means the 2 things that look strangest about Spark when you meet it, that it records your work instead of doing it and waits until the last moment to run anything, are not quirks. They are the direct consequence of that one decision. Next time, we start building.